So welcome everyone. Looks like we have actually quite a lot of people attending Dorsa's talk, which we're all looking forward to. So let me quickly introduce Dorsa. Dorsa is an assistant professor of computer science and electrical engineering at Stanford University, and her research interests lie in the intersection of robotics, learning, and control theory. And specifically, she's interested in developing algorithms for safe and adaptive human-robot interaction. So Dorsa received her doctoral degree in EECS from Berkeley in 2017 and has received a bachelor's also from Berkeley in 2012. And Dorsa has won numerous awards, including the NSF Career Award, AFL-SR Young Investigator Award, IEEE TC CPS Early Career Award, Google and Amazon Faculty Award. And also Dorsa's research, just in the past 2 years, has won 5 Best Paper Awards, 2 in 2019 and 3 in 2020 in Quoral and RSS and HRI. So all these kind of top tier conferences in robotics, in machine learning. So we all look forward to hear from Dorsa today. And so Dorsa, please.
All right, thank you so much. Thanks for the kind introduction, Jadon, and thanks for hosting. So I'm super excited to be here. Let me start sharing my screen. Okay, so thumbs up from Jajun. Can you see it? Yes. Okay. All right, sounds good. Thanks everyone. So really excited to be here today, and I'm Dorsa Sadigh, and today what I want to do is I want to talk a little bit about my work in the space of human-robot interaction. And specifically, I want to talk about how we can use ideas from machine learning and interactive learning, and in general, how the two can inform each other. Like, what can machine learning do for better interactions with humans? And what can interactions with humans actually do for machine learning? So as I mentioned earlier, my research is in the space of human-robot interaction. We usually work with robots that kind of look like this in the lab, collaborate, coordinate with humans for various types of tasks. And if you think about the field of robotics, the field of robotics over the past decade has made a lot of advances, right? Like we've seen all these awesome videos from Boston Dynamics, robots doing parkour and really amazing work. And then on the other hand, on the right side, we see this robot from OpenAI that is basically trying to move the block from one configuration to another configuration. And a lot of these advances is due to having really good controllers and also having machine learning. So the robot on the right is using ideas from reinforcement learning to actually achieve this task. So that's really exciting because we've finally got to a point where we can think about interactions. We can think about intricate and long-term interactions between autonomous systems like autonomous vehicles or robots with humans in their homes, in their cities. And all of these are exciting applications that I think it would be interesting to look at when we have these robots in our everyday homes. But today what I'd like to talk a little bit about is this idea of interaction. And when we think about interaction, the first thing that might come to our mind is human-human interaction. Humans are really good at this, right? Like they easily come to each other's spaces and they collaborate and coordinate with each other, and they can predict what the other agent is going to do and anticipate their goals. They can even influence each other, which is kind of interesting, and I'll get back to that idea of influencing later. And when we think about two humans trying to do a task together, one way of modeling that is to assume that, well, I have two humans, Alice and Bob here, coming together, trying to do a task. Let's say they're playing a game. Let's say they're playing a game of chess. And one way of doing this is to basically model the fact that the other agent has a model of us. So, right, like when you think about playing chess, you think about what would your opponent do? And how does the opponent think about you and your actions? And this is often called theory of mind, and it does show up in a variety of fields, right? It shows up in human-robot interaction, where you think about how the other agent thinks about your actions and so on. But it also shows up in other fields, like in reinforcement learning, right? Like you do opponent modeling, and it has a lot of similar ideas as theory of mind. Or in natural language processing, we have rational speech act and pragmatics, and it's kind of looking at a similar type of paradigm. And the thing about this idea of theory of mind is it works really well, but the problem is it fairly quickly blows up, because fairly quickly, you have to do this recursive belief modeling that is going to be exponential, and it would be very difficult to actually capture that. But regardless, like there are ways of approximating that, and that is actually like how prior work in human-robot interaction does it, how prior work in NLP does it. And specifically in the space of human-robot interaction, we have also done some work where we basically approximate this theory of mind, and instead of worrying about the full game, we just cut it at the nth time step, and we do an nth order theory of mind where we don't worry about the full game. We just cut it. For example, one could think about this as a stack overbreak game where you have like a leader and follower, and you don't worry about the recursive reasoning too many layers down. So this is actually something that we did. This was work that I worked on actually during my PhD, where we were looking at an autonomous car and a human-driven car and how they should like model the interaction between them. And we took like this game theoretic approach there, where we thought about how the actions of the autonomous car, in this case, the orange car, is going to be an optimizer of some sort of objective, but that depends on the human, right? Like that objective depends on how the human acts and how the human like behaves in this scenario. So the human being this human-driven car, this white car here. And a very good question to ask is, well, how do we model this interaction, and how do we model how the human drives? And in this case, we model the human as an agent who is approximately optimizing some sort of objective. I'll come back to this idea a little bit later in the talk. But the point I want to get across here is theory of mind kind of works. We actually like applied it in this setting, and we approximated it, and we ended up getting some reasonable behavior. Like one reasonable behavior that we got was we were able to handle scenarios that, let's say, like this Waymo car doesn't really like handle. So let me show you what the scenario is. So the scenario here is there's this vehicle that's trying to change lanes, it's signaling, and it's not really taking into account the interaction with the other drivers. So no one is letting it in. And because of that, it needs to exit and come back around and try again. This is a somewhat old video, so I think Waymo cars are probably better these days. But the idea is we need to think about interaction, and what we ended up doing by this idea of theory of mind and approximating it was being able to take behaviors that are a little bit more interactive. So we were able to have autonomous cars that were actually able to nudge in front of the other drivers and influence them, actually like make them slow down and have like this game theoretic interaction that allows the vehicle to change lanes, kind of like what this white car does here. All right, so let me go back to this slide. So in this slide, I was talking about how one can model the interaction between humans and robots using theory of mind. But the thing that I'd like to argue in this talk is actually not theory of mind. The thing I'd like to argue in this talk is that a lot of interactive tasks are actually not like playing chess. Like there are a lot of tasks where two humans or a human and a robot come together and they're trying to coordinate on a task, and they don't actually think about what my partner thinks about me and so on. So imagine here I have Alex and Bob coming together trying to do a task together. Imagine they're trying to build a structure together. And in this case, I really don't think Alex is thinking, well, I wonder what Bob's beliefs are over my policy or what I'm going to do next. Instead, I really think what's happening here is that they're keeping track of some sort of shared representation that is much less complex, and they're trying to keep track of this low-dimensional shared representation that is enough for them to achieve the task. And another reason that I argue about this hypothesis is that if you think about humans, right, like one thing we know about humans is that they're bounded rational. And I really don't think they're able to like keep track of these high dimensional beliefs in their head. So they're keeping track of a much lower dimensional thing, when one could think of it mathematically as a sufficient statistic, right? Like what is the sufficient statistic needed to achieve this shared task? And we often have names for this, right? Like a lot of times we call it like roles, who's leading or who's following, or we call it intent, or the person's goal or style. And sure, like there is a lot of work out there that does belief modeling over these types of intents or goals or roles. And that's not what I'm arguing here. Like you might say, well, duh, right? Like intent modeling has been a thing for a long period of time. But the thing I'm arguing here is we should try to directly figure out what that low dimensional representation is. I'm not suggesting we should write 5 like intents and then do a belief modeling over it. What I'm suggesting is we should directly understand what that low dimensional representation is from the interaction data that we have from these 2 agents. And that's kind of like the core of what I'd like to talk about today. Okay? And kind of this common theme throughout the talk is about learning these low dimensional shared representations that capture the interaction. And once we have these shared representations, then maybe those representations are the things that can capture how the interaction changes over time and how we should even adapt to someone, because they're much more manageable as opposed to, let's say, belief modeling or doing theory of mind. And I'm using this icon for it because I don't really know what that is. It's a representation, and it would be interesting to see what that would be in different applications. So going back to this picture, I had Alex and Bob doing a task together, and imagine I would want to have a robot coordinating with Alex instead of Bob. And there are a couple of interesting questions here. One interesting question here is the fact that this agent that I'm working with, Alex in this case, is also a learning agent, right? Like that agent also changes over time, right? The first time Alex is trying a task, his behavior is going to be very different from like the 20th time he's doing it. So that agent is non-stationary, and we should try to be able to capture that when we are thinking about this interaction. So that's one of the core points that I think is really important when we think about this interaction. The other thing is, if I have this robot should be able to actually coordinate, right? Like actually work and coordinate and collaborate with the other agent. Or if this robot is playing a competitive game, it should compete, right? It should interact well with this other agent, being a human in this case. Or even beyond that, it should try to influence. And by influencing, what I mean is kind of this behavior that we saw earlier in the driving example, where the white car nudged in, and by nudging in, it actually influenced the black car to slow down and make room, right? Like black car was going 60 miles per hour, but because the white car like cuts in front of it, it's not gonna go 60 miles per hour anymore. Why? Because it doesn't want to collide. So it actually gets influenced to decrease its speed. And I think influencing is a little bit underlooked in the field. And I think it's an interesting type of behavior that we should think about as we put robots in our world. And finally, the last thing that I think is interesting, and I'm trying to bring that to this space, is this idea of shared representations, latent representations that capture either the task or the partner that can help us actually do this task much more scalably and much more effectively. All right, so for the rest of the talk, what I want to do is I want to talk about a few topics. Mainly, I want to spend my time talking about this idea of learning latent representations of the other agent. I'm calling it latent intent. And then how this learned representation can help us coordinate or influence and can help us actually address non-stationarity. So in the first part of the talk, I'd like to actually focus on how we are addressing these 3 kind of core things using this idea of learning latent intent. Then, depending on the time, I probably won't have too much time to talk about these 2 other topics, but these 2 other topics are about how we can learn from humans. So how can we learn human preferences? I'm going to spend a little bit of time talking about that. And then the last topic is about, again, using these representations in a particular application of assistive robotics and how that can be helpful in that particular application. Okay, so let's just jump into it. All right, so I've been arguing that when we are coordinating with other agents, these other agents, they're often learning agents and they're often non-stationary. And what that means is they're going to update their behavior in response to the actions of their partner or the robot. Okay? Let's think about a concrete example for this. So imagine we have an agent, a robot, let's call that an ego agent. So that's our learning agent. And then we have another robot, let's call that the other agent. And let's say that these 2 robots want to play a game of air hockey together. Okay? So the way I'm thinking about this is that this other agent might follow a policy. Let's say it follows a fixed policy. And the fixed policy is it's either going to push the puck to the left or to the right or to the center. Okay, so it's following some sort of rule-based policy. And then a trajectory, I'm going to call that tau, is going to be a sequence of state and actions that this ego agent actually observes, and the rewards that the ego agent gets. And the reward is going to be based on some sort of distance metric, as well as the fact that if you're able to block the puck or not. So then basically the strategy of the other agent could be represented by this function f, and I'm representing that using z. So z is going to represent the strategy of the other agent that depends on the trajectory and also depends on what it has done in the previous step. So specifically the way we are hand coding this f, so we're hand coding f to be that the other agent pushes the puck toward a different direction if the puck gets blocked in the previous time step. Okay? So if the ego agent is able to block it, then the other agent changes its strategy and pushes it toward the other direction, toward another direction. And this f function, as I said, it's rule-based, and that's what the other agent follows. But the ego agent, which is again my learning agent, does not have access to it, does not observe it in any ways. Okay. So what we're trying to do is we're trying to come up with an estimate, with a representation of the other agent or the partner's policy. And the way we do that is by trying to use ideas from representation learning, where we look at the past trajectory, so the tau at time step k-1, and we're trying to encode that into a low-dimensional representation that captures the policy of the other agent. So this zk is going to be really what the robot thinks, like captures what the robot thinks the other agent would do. Would it push it to the right or left or center? And the way we learn this zk is by training this network, so we can decode zk in order to predict the next trajectory. Okay? So our loss function is going to look something like this, which is kind of a prediction loss, where we are, based on the past trajectory, we want to be able to predict what happens in the next time step, next trajectory time step episode. And basically this zk, I'm going to refer to that as latent intent or latent strategy of the other agent. Okay. So now that I have this representation, right? Like now that I have like these trajectories, I can encode them to a representation of the policy of the other agent. I should be able to use that, right? This zk, this latent intent, is again an estimate of what the other agent is doing. Again, this is like as opposed to, let's say, if I were to do theory of mind, where I would do belief modeling. This is a representation, a low-dimensional representation of what the partner does. But now I can actually use this representation for planning for the ego agent, right? At the end of the day, ego agent needs to figure out what to do. And one way of doing that is by using, let's say, reinforcement learning. So what the robot can do, what my learning agent, ego agent can do, is it can maximize the expected reward based on a knowledge of Z, and this Z is learned through this representation learning component. Okay, we're calling this algorithm learning and influencing latent intent, or LILLY. And what LILLY does is it's going to maximize expected return within an interaction, and by doing so, it's able to react to the other agent. It's actually able to coordinate with the other agent. Let's see how LILLY works in an example. So let me give you a concrete kind of abstract example. So imagine that we have a point mass example where we have, again, two agents, ego agent and other agent. Okay? An ego agent is an agent that starts from somewhere inside of the circle, let's say here, and T here shows our time steps, so T1, T2, until TH. And the ego agent basically starts from somewhere inside of the circle and moves towards the boundary of this circle. And we have this other agent, and what other agent does is it can either move clockwise or counterclockwise around the circle. And the way we are formulating this is that if the ego agent ends up inside of the circle at the end of its trajectory, the other agent follows this counterclockwise behavior. But if the ego agent ends up outside of the trajectory, the other agent moves clockwise. So our actions, the actions of the ego agent, influences the policy of the other agent. Okay? All right, so in this example, if we run state-of-the-art reinforcement learning, let's say soft actor critic, the behavior of the ego agent is going to look something like this. It's going to start from here and then end up in the middle of the circle. The reason is soft actor critic is not really modeling this partner or this other agent. And because of that, the best strategy it can do is it can kind of like just go in the middle of the circle to minimize expectation, depending on the other agent going to the right or to the left. And that's the best thing we can get. But if you're following our algorithm, LILLY, what happens is that our agent starts from somewhere inside of the circle, and then it's able to go ahead and capture the other agent through like optimizing its own reward, and it's able to basically like mostly get the other agent in this circle example, point mass example. Okay. Let me show you what happens in the air hockey example. So in the air hockey example, let's say that we define the reward. So you get a reward of +1 if you're able to block the puck. Again, the ego agent gets a reward of +1 if it gets blocks the puck. And we kind of like make up the scenario. So you get a reward of +2 if you're able to block the puck on the left. So this is like we are saying our ego agent like gets more excited if it is on the left, and it really prefers to block the puck on the left. So because of that, we are giving a reward of +2, making up this example when the puck is blocked specifically on the left. Okay. So if we use soft actor critic, so the initial policy starts off, and at some point after a couple of hours of training, like 2 hours of training, it's able to block the puck, right? So if you and it's able to block the puck only on one side, because soft actor critic, again, remember, it doesn't model the other agent, so it just becomes good at blocking the puck at one side, and specifically in this case, it's blocking the puck on the right. But after like 4 hours of training, soft actor critic realizes that, oh, if I actually go to the left, I get more rewards, because remember, like we artificially said, you get reward of +2 if you go to the left. So it eventually converges to the fact that I'm always going to go to the left because I get more rewards there, and I'm not modeling the other agent, so I wouldn't know like how to basically use this model of the other agent. So you kind of like see the behavior of soft actor critic here. Y-axis is success. So we get like around like 40% success. It starts off blocking to the right, and at some points it's like, oh, I should actually go to the left, and it blocks the puck on the left, and that has success rate of around 40%. We uniformly like get the robot to go to the left or right or center. They got lucky, and he got around 40% success rate. If you're using LILLY after 4 hours of training, what happens is that LILLY is able to actually model the latent strategy of the other agent. And because of that, it's able to block the puck, like no matter where you send it. So in terms of success rate, you're going to get around like 90% success, where LILLY captures, again, the model of the other agent, and then is able to like go either direction and block the puck, depending on where the other agent sends it. Okay. All right, so far I've been talking about this idea of reacting to other agents, right? So what was the idea? Just to recap, the idea was we have a reinforcement learning agent, our ego agent, our robot, our point mass example. And what it wants to do is it wants to optimize a reward. But the thing is that reward depends on how this partner works, or how this, I'm calling it other agent. The reason I'm calling it other agent is it doesn't need to be a partner or opponent. This framework works in both competitive and collaborative settings. That's why I'm calling it other agent. But yeah, the idea is my ego agent is optimizing its reward, and its reward depends on the other agent's strategy, but I don't want to model everything about the other agent. Instead, I want to capture a latent representation of what the other agent does, and that latent representation is going to be captured by this representation learning component, capturing the sufficient information that I need about the other agent, and that goes here. Okay? So that was great. We were able to react to the other agent. All is good. But we can even do better. And by that, what I mean is, instead of maximizing the expected return within an interaction, we can actually maximize the expected return across multiple interactions. And the effect of that is going to be going beyond reacting, and we would actually be able to influence the other agent towards behaviors that are useful for the ego agent in the long term, or for the team in the long term. So what does that mean? So going back to this point mass example, remember, LILLY was able to capture the other agent, but this wasn't the best thing for LILLY, because LILLY was like this agent was this ego agent was being penalized for the time that it takes to get to this boundary. The best thing that this ego agent could do is to influence the other agent to end up somewhere close to it, so it can travel the minimum distance possible and capture the other agent. And that's actually what we see when we incorporate influencing, where we optimize like the reward across interactions, and our agent is able to go and capture the other agent and influence the other agent, so it travels the least amount of distance. going back to the air hockey example, so when we do LILLY with influencing after 4 hours of training, it's not only able to block the puck, but it's also able to influence the other agent to push the puck toward the left, because remember, it was getting more reward if it goes to the left. So because of that, it kind of like makes the other agent behave in a particular way that's useful for it. So going back to this plot, if we think about influencing in terms of success rate, it is going to be similar to LILLY with no influencing. It actually takes a little bit longer to train it, but eventually, like in terms of success rate, it's around 90%. It's kind of like a similar behavior. But the difference between influencing and not influencing is the number of times that we get the other agent to push the puck to the left is going to be higher in the influencing case versus the no influencing case, where we're not doing that, and then it's like uniform across left, middle, and right. Okay. All right, so let me just summarize the key takeaways here. So I've been talking about this idea of human partners or other partners that we're working with being non-stationary. That is, they follow a strategy that changes over time, and like I don't have like access to that strategy. And what we've shown is that we can represent that using low-dimensional latent strategies that are kind of manageable, and use these low-dimensional latent strategies in order to better anticipate what the partner does, to react to them, and also influence them so they behave in ways that are better for our reward or for the team's reward. And I think that in general is very exciting. But we were motivated by this because we wanted this robot to work with humans, right? That was the whole point, right? Like we wanted to capture humans' non-stationarities and latent strategies. And so far, everything I've shown you is about two robots playing air hockey together. So we did actually try out our algorithm with a human, and we were able to get like around like 70% success rate here. It was worse than the case where we have two robots working together. And part of it is that the human strategies and kind of behavior in general is more subtle. And it was incredibly difficult to train this robot with a human in the loop, right? Like this robot was running a deep reinforcement learning algorithm, and there was just not a practical way of bringing the human inside of the loop of training here. Because like, as I showed, these robots were training like 4 hours overnight, and it didn't really like make sense to train with the humans. So the challenge here is that it seems kind of impractical to bring humans inside of this learning loop. And a good question to ask is, well, can we do better? And if we actually want these robots to work with humans, right? Like, what should we do? Like, what is the path forward? And with that, let me go back to my diagram, my outline diagram. So far, I've been talking about this idea of learning latent intent or latent strategy of the other agent, and it does capture non-stationarity of the other agent. We showed coordination and influencing, and we showed how low-dimensional representations can be useful there. But the thing we didn't really like handle was the fact that, hey, there's a human here, and we should try to learn from that human. And what I want to talk about next, and maybe a little bit briefly, because I think I only have like 15 minutes, is this idea of learning from humans. So this is all great, but what if I actually want to learn from humans? What if I want to be able to figure out what humans want or what humans want robots to do, and learn that? And for that, I'm going to talk a little bit about some of the ideas we have been exploring around learning human preferences and reward functions. And I'm going to simplify everything. I'm just going to talk about learning from humans. I'm not going to worry about non-stationarity. I'm going to assume humans have a fixed preference or reward function. I'm not even going to worry about what the robot does in response to that model. And then I'm dropping the latent representation idea for a second too. So let's just think about how we can learn from humans. So the idea of learning from humans has been around for like at least like 2 decades in the field of machine learning, even longer in the field of control theory. It goes back to Kalman, this idea of like inverse optimal control. And the idea is, if I can actually collect demonstrations from an expert who can do a task, maybe pick up an object, then maybe I can learn from those demonstrations some sort of objective that the human wants the robot to follow, or some sort of policy, and then the robot would be able to do the task the way the human wants it, right? This is called imitation learning. And the issue is, like, the big assumption in most prior imitation learning work is the fact that there has got to be an expert here, and these are expert demonstrations that are super perfect, and they are demonstrations. But the idea, the key idea that maybe I want you guys to get away from this part of the talk is that is pretty restrictive. And one can go beyond that by tapping into many different sources of data that exist from humans. So expert demonstrations is not the only thing we have access to. A lot of times we have access to many other types of data that would be useful to learn from, or even like suboptimal data or observations, right? Like what if I have just like a bunch of observations of people cooking, like people's cooking videos, right? It's not like perfect expert demonstrations, but the question is, can I be able to learn from that? So can we learn from a diverse set of data sources? And for that, we've been looking at a variety of directions in my lab over the past couple of years. So expert demonstrations is definitely one of them. More recently, we have been looking at this idea of learning from suboptimal demonstrations and observations and how we can rank trajectories based on how useful they are. We also have like a new thread of work around thinking about language instruction. So I have a student who is kind of in that robo-NLP space, and we are thinking about how to use narrations or language instructions along with demonstrations and how the two together can help us better learn what humans want. Something we have been working on for like the past couple of years is this idea of pairwise comparisons and rankings and how we can learn human preferences about when the robot shows them a few trajectories. So the human doesn't need to provide a trajectory, but the robot just generates trajectories and asks for comparisons and rankings. And that has a lot of interesting questions in that space that we can learn reward functions from. And finally, another direction that more recently we have been thinking about is learning from physical correction. So a robot is pretty different from an AI agent, right? It has an embodiment, it has like a body, and you can actually like move it, right? Like if you move a robot arm, right, like that has a lot of information in it. If it like brings like a coffee mug like from all the way up here and you actually like push the robot arm down, you mean something by pushing that down, and maybe the robot can figure out what humans' preferences are through those physical corrections. So I'm not going to go into any details of these. Maybe I'll just briefly, very briefly, talk about some of our work around learning from pairwise comparisons, and that's the core thing I want to spend a little bit of time on. So what I mean by pairwise comparisons is that I can just show two trajectories to a user, like A and B, and then instead of asking a person come and demonstrate something, I can just ask a user, well, which one do you prefer? Kind of like movie recommendations, right? Like, which one do you prefer? Do you like A or do you like B? And based on that question, I can learn something about this underlying reward function that I assume the human follows. And this underlying reward function, let's say, is parameterized by some parameter theta and has a set of features. I'm writing it as a linear combination of a set of features, but it doesn't need to be linear. We actually have some work where we consider nonlinear versions of this. And the idea is, if I imagine the parameters lie in, let's say, a three-dimensional space, every question, every query that I ask from a user generates a separating hyperplane in this space. And the human's response, the human telling me, hey, I like A over B, tells me which side of the hyperplane is preferred. And then based on that, the interesting research question for us is, what is the most informative, diverse sequence of questions that I can ask a user so I can quickly figure out what they want? So in general, like, I think this can be a way of addressing the issue of lack of data from humans, right? Like part of the reason that we can't do learning with humans in the loop is it's just really difficult to get data from humans when they're interacting with robots, or in general, like when they're like interacting in the world. So instead of just blindly collecting data, I think it would be interesting to look for the most informative data, the most diverse data point that help us actually like address the problem that we have at hand. And then for that, we are using ideas from active learning, where we have like a series of work where we basically try to actively generate the most informative, the most useful question, as opposed to any question, so that we learn this reward function as fast as possible. So all this equation is saying is, ask a question, phi corresponds to a question, that maximizes the volume that would be removed from the hypothesis space of possible like reward functions that you might have in your mind, subject to the fact that it's feasible and works on the real robot and things of those forms. Okay. So here's just like a toy example of showing that on a robot, on an autonomous driving, like 2D autonomous driving setup. So the idea is if you don't ask any questions, you have this orange car that doesn't really know what to do and kind of like moves around randomly. But after 30 questions, these are binary questions, the car learns how to keep heading. And finally, after 70 questions, the car learns kind of how to drive in this 2D space. And I think that is exciting again, because there are no demonstrations here. This is 70 binary questions. And based on 70 binary questions, I can figure out how I can learn a general reward function that would actually work in any other scenario that requires collision avoidance and keeping in lane and so on. And I think that part is, and I think in general, like we should think about how we use preference data and incorporate all these data to learn reward functions. All right, so I'm going to skip this idea of the learning from other types of data like physical corrections. That's something that we are in general have started working on, like the fact that maybe you have like a grocery bag and the person can like pushes the arms and based on those pushes and pulls and sequence of corrections you get, you might be able to learn a reward function. I think in general, like that's another source we should tap into, but I'm going to skip the details for that. All right, so what I've been talking about so far is that we should learn from humans somehow. And one way of doing that is that there are many different sources of data that we can tap into, and humans tend to leak information through like all these different sources. So we should use those information like suboptimal demonstrations. But in addition to that, we should actively query them and look for the most informative questions to learn, let's say, reward functions as a way of capturing their preferences. So what I want to show you very quickly for the last part is this idea of still being able to learn from humans, but bring in that key insight that I had early on, which was about using latent representations, because that allows us to capture something that's much more scalable, much more efficient when we think about interaction between the human and robot. And I'm going to talk about this idea of coordination for a very specific task of assistive robotics and assistive teleoperation. And I'll briefly talk about that and I'll wrap up after that. All right, so we got excited about this domain of assistive robotics and assistive teleoperation, which is an interesting domain. So actually more than 1 million Americans use these wheelchairs that have an arm on top of them. And they use them for various types of tasks like getting outside of the bed or feeding themselves or bathing. And here is actually one person using one of these arms in practice. So he's trying to open the fridge. And the thing I want you guys to look at is his hand, his right hand, right here. So he keeps pushing the side. And what he does by pushing the side is he's changing the mode of the end effector. So the way he's controlling this robot is that there's this end effector, end of the robot, right? And that has 6 degrees of freedom or 7, depending on the robot. And what he's trying to do is he's trying to control like the XYZ of the robot, the linear control, and then the yaw, pitch, roll, the angles of the end effector. And when he's pushing the side, he's switching between the linear and angular mode. And that's why it's like pretty difficult, this mode switching and kind of like controlling 6 things at the same time is pretty annoying and pretty difficult for this person to do. So our insight here was that if you think about robot arms, assistive robots, they're dexterous, and this dexterity actually is the thing that makes them useful, but is the thing that makes them hard to control. So the question is, could we have a better way of controlling these robots? And specifically, we're going back to the old idea of learning low-dimensional representations, right? Can we have a low-dimensional representation that can make controlling these robots much more easier and much more intuitive? And at this point, right, you might say, well, why do you have such a hope, right? Like if you want to get the arm to go from any point in the state space to any other point in the state space, you kind of need all those degrees of freedom. There's a reason they exist. So why do you think you could learn a low dimensional representation that does the job? So our insight really is that we should be able to learn that conditioned on the task. So as an example, imagine that I have like a high dimensional robot arm. This is a 2D robot arm, but it has like many joints. So I have to control all these joints. And I really want this robot to move on a sine wave. And one way of controlling that is to control all these joint angles, right? Like say, what should be the joint angle for everything? Like a 6-degree freedom controller. Another way of controlling that is to have a 1-degree freedom controller that says, hey, +1 goes to the right and -1 goes to the left, because I already know the robot should be moving on a sine wave. And then that is kind of like the key insight, context, right? Like state. So if we can condition on the context, on the task, we should be able to learn a much lower dimensional representation that is much more intuitive for the person to use. And that's exactly what we did. So here, similar to before, what we did was we trained an autoencoder exactly like before, but this time we conditioned it on the state and belief. And then we were able to learn a low dimensional latent action that's able to get the robot to do various types of tasks in this space. Okay. Let me just show you how this works in practice. So here I have end effector control on the left, which is what I talked about earlier. You're controlling 6 things. And you have latent actions on the right, which is our algorithm. You're controlling 2 things at a time. And this user is having such a hard time on the left trying to get the robot out of like this mode. And then on the right, it's just like much more smoother, much more easier to move between the shelf and move things around. And we're looking at this long horizon task of making an apple pie. And at the end, you're supposed to steer. Everyone does their own weird way of steering. But as you can see, again, much more intuitive and faster to use low dimensional representation where you're controlling 2 things as opposed to controlling like 6 things. And I think that is very exciting, this idea of being able to capture what humans want in a much more effective manner when we think about interaction between humans and robots, let it be assistive teleoperation or let it be like more dyadic settings like the air hockey example that we saw earlier. More recently, we've been thinking about integrating shared autonomy with this approach and making it easier. We've also thinking about assistive feeding these days, which I think is a very exciting area. I think it's a very exciting area from a robotics perspective, like picking up food and deformable objects, and also then thinking about safety and comfort and bringing the food to the person's mouth. All of those are very interesting questions that currently we are working on. All right, so let me wrap up. So what have I been talking about? I've been talking about the fact that when we think about interactions between humans and robots, humans are non-stationary. We should be able to capture that. In addition, the robot should be able to coordinate and even influence sometimes the human. And one of the core ideas that I've been talking about is there should be a way of capturing what humans do that's much more manageable than doing recursive belief modeling. And specifically, I've been talking about this idea of latent representations and how these latent representations can capture what humans want in dyadic interactions, like we saw in the air hockey example, in assistive settings, like we just saw in the previous example. And I've been also talking about the fact that if there is a human in the loop, we should try to learn from them. And one way of doing that is using more active methods of learning what people want, or kind of like tapping into different sources of information that humans give us. And this was kind of like my table, but I really think we need like all 4 of these, right? Like, and in these last works, right, I assumed non-stationarity. And to wrap up, I just want to go back to this idea of non-stationarity, because it does show up everywhere. And again, it's a little bit underlooked, and I think it's incredibly important. It shows up in the setting of assistive robotics, for example, like in the setting of like exoskeletons, for example, when these exoskeletons are usually used in rehab when people are trying to like use them to help them walk or learn to walk again. And then when people use these robots, right, usually like they're learning. The point is they should learn how to walk again. And one of the biggest problems in this space is over assistance, where the robot doesn't capture the fact that the human is changing, the human is adapting, and just like helps them walk, and it wouldn't allow the person to learn some of the skills. Another place that it shows up is in driving, right? Like I was talking about the fact that you can nudge in front of someone and cut in front of them, but we should think about what would be the effects of that, right? Like if I cut in front of anyone, like they might get really angry and come back around and try to get ahead of me. So I can't just like cut in front of anyone and influence them. So we should like think about the effects of our influencing on humans and non-stationarity of them and how they change over time. One example that I personally have experienced is driving around autonomous cars these days. So this is a picture from San Francisco. I used to live in SF, bike to 4th and King to get to Stanford. And one of the issues there is when you bike around these cars, like specifically cruise cars, at least they used to get stuck at intersections like all the time. And what you do is you just go around them because you think they're stuck. And that's kind of crazy to me, because based on that, like 3 interactions that I've had with a cruise car, I've decided to change my behavior. I've decided to just go around this vehicle. I'm giving wrong data to Cruise. Cruise is going to think bicyclists are just going to go around it. And then, yeah, like my behaviors have adapted, and these autonomous cars should actually capture like how they are affecting people, as opposed to, oh, just making a nice car that does driving. Like they should think about interactions a little bit more. And it might be okay in like a one-time interaction, but imagine when you have like a fleet of autonomous cars, right? Like Waymo is trying to put fleet of autonomous cars on the road. I think it would be interesting to think about what would be the effects of these autonomous cars on some of the longer term things, objectives that we care about, like how that affects things like traffic. So we have like a whole thread of work on mixed autonomy traffic that I didn't talk about in this talk, thinking about how when you put autonomous cars on the road, how that changes people's incentives and routing decisions, and how that influences like the team of humans. And I think that's a very exciting area to work on. So with that, I'd like to thank the group. This is the group during the COVID time. And thank you guys for listening. And I can take any questions.
Great. Thank you so much, Dorsa. Yes, it's a wonderful talk. We actually have quite a few questions. The first one, actually from the research director of HAI, Deep. He was curious, if I understand correctly, for the LILLY portion of the talk, the other agent chooses trajectories based on known function, f, but the ego agent doesn't know this function, and instead it learns an autoencoder, which encodes the tk minus 1 into zk, the latent vector, and then make decisions based on zk. So then the question is, if the function, the known function that other agents use increases in complexity, so how does the performance of the ego agent change? How about the ability? Would it be harder to learn the correct Z, the latent representation?
That's a very good question. We've actually like tried that. So yeah, the function that I've shown here is pretty simple, right? It's just based on the previous time step. Like, what would you do? You change your behavior. But in practice, yeah, so you could have much more complicated functions. So we have actually tried out functions that have a longer dependence on history. So like on the previous 3 time steps or 4th time steps or 5th time steps, or what if they pick like the majority rule? So we've actually played around with like adding history, and it actually still like performs better than all the baselines, but the performance does go down when you make this function much more complicated. The extreme level of complexity would be that the human acts randomly, right? Like if you think about this particular like air hockey example, it is kind of like rock, paper, scissors. And the best strategy in rock, paper, scissors is to actually like play randomly. So the extreme would be the other agent plays randomly. And then if you're able to, if you want to capture that, our strategy basically boils down to what soft actor critic does. So it would just like go in the middle, because there isn't like any model of the partner that would be helpful.
Yeah, that makes sense. So another question is, what are the limitations of the specific representations you have adopted for modeling the latent states, the latent representation based on Markovian encoder-decoder setup? What happens if the opponent is maximizing an infinite horizon partially observable model? Maybe that's similar to what you just talked about, actually.
Yeah. So it would just like boil down to soft actor critic. Yeah.
Okay. A practical question, which maybe
something on that. But the argument that I guess the reason that motivated us to work on this is, if you think about collaborative tasks. So this is a competitive task, and you might want the best strategy for the other agent, which might be like play randomly in this case. But if you think about collaborative tasks, like 2 agents trying to move a table together, right? Like in those settings, it's actually pretty difficult to have 2 robots that are decentralized do the task together. Like they have to do theory of mind, belief modeling, all of that. It's really difficult. Humans just like easily do it, right? Like you get like a small cue, like a small push from the person, and then you just know what to do next. And kind of like our motivation was that like that small push, right? The fact that I can understand that small push, that means that there is a low dimensional representation here that could help us coordinate better. And collaborative task, like I think we should try to capture that and coordinate.
That's interesting, because you're saying essentially, when humans are collaborating with each other, there are kind of a relatively low dimensional representation that you can use to make decisions, and the trajectory or whatever that function F that other agents use couldn't be too complex, or at least should be able to be encoded in a relatively low dimensional representation.
Exactly, exactly.
That's a nice argument. A practical question is, I'm also curious. So I would like to purchase a robotic arm for learning robotics and programming as a hobby. So I assume you showed us 2 different robot arms. Is there anyone that you think is particularly affordable for someone who would like to start experimenting with those things?
It's a good question. So I don't want to like advertise companies here, but we have been using these panda arms that I think are pretty like good. So like I showed like in the air hockey example, I showed the 2 panda arms playing with each other. And I think they're relatively more affordable than other like high degree freedom robot arms that are out there. Affordable is like under like quotations affordable, but they're pretty good too. Like they have like really good like torque controllers and all that. So I've been like pretty happy with those. There are much more affordable ones like under like 1K, 2K. I forget the company's name, but they're not like as fancy. But we use like some of those arms for like education and things of those form, or just like playing around as hobbyists. If you shoot me an email, I'll find out the name of the company and send you a link.
Okay, yeah, great. Yeah, another question is, can any ideas from coordinating influence in your robotics work apply to general domains, such as steering low-dimensional representations of generative models of images, text, videos, and audios to generate media more directly aligned with human preferences?
That's interesting. Yeah, so I haven't thought about the specific application that or direction that was brought up. But we are thinking about this idea of influencing much broadly. For example, one space that we are looking at it is in training multi-agent reinforcement learning agents. So like in the training phase, we are thinking about how influencing could guide you to end up in better equilibria. So imagine you have like a multi-agent system, and if you just run multi-agent reinforcement learning, assuming it converges and all, it could end up in, let's say, 2 different equilibria. And both of them are assumed like both of them are like Nash equilibria, both of them could happen. And maybe one is preferable for one reason. And what we are looking at is how we could use some of these influencing ideas during training. And specifically, there's this idea of gifting. So how you can like gift rewards to the other agent, like bribing really. So how you can bribe the other agent to push the other agent towards like a better equilibria and kind of like a long-term type of behavior. I think it would be interesting to look at it in some of the domains that are mentioned too.
Yeah, that is indeed an interesting question, also from Deep, because that reminds me of, think about HAI and it's like, okay, how AI can work with humans, and there are 3 different pillars. And if what you're saying, the fundamental idea is the human preference or intent can be encoded as a low dimensional representation, then maybe that can be a kind of very inspirational to all those different AI works. How, if you want to impact humans, then you have to understand what is the human intent in that situation as well. So maybe there's a broader application. The general idea can maybe be applied to very different domains.
Yeah, that would be really cool. Yeah.
Okay. So I guess a few more technical questions. We still have 5 minutes. One is, in the end effector low dimensional example, what is the state dimensionality in low dimensional representation is conditional? Sorry, let me find it. Would it also work on higher dimensional state encoding, such as the states based on sensor images?
Yeah, so for the last work, right? Yeah, so I think that's referring to the last work where I talked about conditioning. So let me clarify something. I think I went over it a little quickly. So there we are learning a low dimensional representation of actions. So it's actually like high dimensional actions where you have like a joystick and you're controlling like 7 degrees or 6 degrees of freedom. And we are doing dimensionality reduction over that to 2 degrees of freedom of joystick again. So we are reducing action space. We're calling it latent action. And we're conditioning it on the state. The state in the very first work that we tried was like encoded as like locations of objects and all that. We actually have a follow-up work that we submitted to L4DC, which is exactly like about images. So like what happens that if I encode, like if I put in like an image of the scene as the state, and it actually like works fairly well, this idea of latent representations.
I see. Let's see. So there's a question saying, based on hand kinematics, we know that there is always a low dimensional representation for hand, because the hand synergy. So the question here is why we need to condition based on action. Do you think the low dimensional representation is always beneficial regardless of the action? Not sure.
Regardless of the action, I didn't catch the second.
I don't think I fully catch it either.
But maybe let me just add like an explanation of why we are doing this, because there is actually quite a bit of work that tries to do representation learning like directly from like your kind of like muscle movements and things of those form. And yeah, there's like a lot of work in haptics too that tries to kind of like just capture that and control a robot. There's like a lot of work from like Antonio Beaky's lab and lots of interesting work there. Similar like ideas. The reason we are looking at joysticks, like joystick actions, and reducing dimensionality for that is we are specifically working with patients with disabilities. And these patients with disabilities have specific like interfaces for controlling the robot. And a lot of times they can't even like move their hands. So we don't really like have access to that. Even joystick is like a stretch. Like a lot of times they use like sip and puff devices, which is like already like a 2-degree freedom controller. So we were a little bit limited to specific population we're looking at, and that's why we're looking at actions and reducing action.
Yep, makes sense. There's a question on, so you're saying you try to model agents or robots that understand the preference or intent of humans, but have you thought about how humans can also understand the robot's intent?
Yeah, that's a very good question. Yeah, we have done some work on that I didn't really like incorporate. It is really like a two-way loop, right? Like how would the human understand robots' capabilities or robots like preferences, or like why is robot like picking up the object like this? There's actually a bit of work also like from Anka Dragan, like at Berkeley, that works on this idea of legibility. So I think a lot of ideas came from like legibility, which is like when you're picking up an object, you should think about what is understandable, expressive for the person, and maybe use like exaggeration to pick up the object. The thing that we have specifically looked at is capabilities. So like robots, basically what the human thinks about the robot's capabilities. And we had like this interesting work, which was about trust. And it was kind of like a coordination task. You and the robot, let's say you're trying to like clean up the table or like set and clean up the dinner table. And basically the idea is based on your model of what the robot is capable of, you might help more or less. We looked at influencing there. This is like a very interesting work that I don't necessarily suggest you should do in practice, but we looked at how the robot can influence the human to make the human think robot is not capable of some tasks, so the human would help more. So I think it was like a made up example, but it was kind of like interesting that the robot was tricking, like almost like tricking the person into thinking robot can't like move a plate, so the human would move that plate.
That's yes. I'm curious. I should look into that paper. Okay, I think we're out of time, and there's still a few questions that are pretty interesting, but unfortunately, we don't have time to go through all of them. But for people who ask those questions, please feel free to email Dorsa, and I think hope Dorsa will get the time to respond.
Yeah.
Okay. So yeah, nice to see everyone here, and yeah, I think this is like the end of this HAI seminar, and thank you again, Dorsa. This is great.
Thank you for hosting, Jajan, again.